Hello everyone, my name is Christian Sanchez and I'm going to show you my finite element method project, which is an application I developed on MATLAB and is capable of solving problems of n degrees of freedom. However, it has implied a graphic user interface that will solve up to 3 degrees of freedom of the problems of an spring, a bar, or a beam. However, as I told you, their functions work for n degrees of freedom, so it might work if you want to add much more types of analysis, like three-dimensional analysis, considering rotational directions and everything like that. So the first thing I will show you how does this works, how does the program works when you are solving a spring problem. Uh, for to do this, I will use a one-dimensional problem of a spring that is shown to you on this slide. As you can see here, we have 3 elements: the element 1, the element 2, and the element 3. And we only have 1 degree of freedom. This means that the the displacement of the nodes and the displacement of each element is going to be only in one direction, in this case in the x-axis. So with these properties and values that we have here, we just need them to introduce on the application. As you can see here, we have the type of analysis. We have to select the spring type. We set up the number of elements. There are 3 elements, which node are subjected to each element. As it's important to save each value that we are setting up, of course. Then we have to set up the properties of each node. Each node has the position, the forces, and the type of boundary condition, depending on the forces that are not needed to set up if you are considering a fixed boundary condition, because there are the forces must be the known forces, and most of the time the known forces are on the free ends or free boundary nodes. So that's why I'm putting here only when the boundary is free. I set up the value of the force. We save the values of each node and then we press solve, and it will automatically solve the problem. It will give us the global stiffness matrix, the forces, and the displacements on each node, and will also give us a diagram of how the element is of this problem. It's just for knowing approximately how does it works. So we know that these values are correct because first of all, the summatory of forces is equal to 0. As you can see here, you just sum every and each value and you will get 0. And also you have that the displacement of each node depends on the boundary condition. As you can see, the only node that is displacing is the node number 2, which is the only one that has a free boundary condition. The other one is fixed condition, which means that there won't be any displacement, so it's a good solution. The next thing I want to show you is how does the type of analysis of a bar works. We need to know the Young modulus, the area of each element, which is, these values are global for this problem here, the number of elements that you have, the nodes that are connected to each element, the force, and the length of each element. So we have all the values. We just need to set up on the following problem. We do the same. Select the type of analysis is a bar analysis. There are 3 elements here. We have to select each element that we are using uh, on the element and the length of each element. And it's important that you consider that every single time you just put the values are on the same same type of measurements. You cannot put a length of feet when you are using PSI, which is pressure per square inch. So you have to put, if you're using pressure per square inch, you have to use the length in inches and the area in inches too. Now we are setting up some boundaries for the problem. Uh, for the node 1, as we saw, uh, there there was a free boundary condition, and we are now considering a bidimensional analysis. So that's why the forces is a vector which has 2 values. The first one is going to be always the x value. No, I'm sorry, the force on the x-axis. The second value might be the force on the y-axis. And if you are working on 3 dimensions, it would be the force on z-axis. I'm sorry it took a lot of time setting up some values here because I made some mistakes while doing this. However, we just can see now what are the values and the solution here. You can see you have the matrix here, the global stiffness matrix here. The graphic is the same as we have seen before. We have the same we have the forces here, the displacement here, and we also have the stresses of each element from 1 to 3 here. Now I will show you also how does it works when you are using a 3-dimension problem. It's almost the same. The only thing that changes, I'm sorry, I'm going a bit faster, but is in the position that you will just put a vector of 3 points, as you can see here. I'm saving it, then I put the other values of each node, and then I solve it. Uh, then I press solve, and it automatically solves the problem. The graphic is the same as this one. You can see that the values of the forces are here, the displacements are here, and as I told you, there are 3 degrees of freedom here. So it's the x, the y, and the zeta axis. And the the only node in which you will see a displacement is in the 4 node, and you only see a displacement in the x-axis that is displacing 0.0086 inches, and it's also displacing on the z-axis minus 0.0068 inches. On the y-axis there is no displacement, and due to the fixed boundary conditions there are no displacements on the other nodes. At last we are solving the beam problem, which is shown to you on this slide, which we are considering that we have 1 element, 2 elements, 3 elements, 4 elements. And if you want, you just can use the equivalent forces of this one that are placed on these parts of the nodes. However, I consider it that is much easier if you consider that there are 4 elements rather than 3. So this is why I am doing this. And I will set up the data of the beam. There are 4 elements as no, I mean I am considering that there are 4 elements because it is much easier for me. The Young modulus is the same of each part of the beam, also the inertia. However, the length is going to change through each element, so we will change the length. It will be 3 for the element 1, 2 for the element 2, 2 for the element 3, and 3 for the element 4. As you can see here, we are also placing the values of each node in which this element is subjected to. For element 1 is subjected to element 1 and 2, the element 2 is subjected to 2 and 3, and so on. Now we set up the boundary conditions, the position, and in case it's a free or joint end, we set up the forces vector, which are the ones that we need to solve these problems. I will make it a bit faster so you can see the conclusion of the data. This application is not showing you. However, no, I mean the video is not showing you that the application has also a pop-up window that asks to you for the maximum distance from the center to the beam, and also it asks for you to tell you how many degrees of freedom does the beam analysis have, in case you wanted to do beam analysis in 3 dimensions. And as you can see here, we also have the global stiffness matrix here. You have the forces, the acting forces here. You have the displacements of each node here, which, as you can see, in the only place that you are having an actual displacement is on the node 3, but on the other nodes the only displacement that is here is like an angular displacement. This means that it's a rotational displacement that are having on node 1, node 2, node 3, node 4, and node 5. And also the stresses here. I consider that the distance from the center to the last point is 0.5 inches. However, it would change if you are using another values, if you are using another, if you're using different types of distances. In case you are using like a beam that does not have the same area, cross-sectional area, and so on. So thank you very much. I hope you like my presentation. I hope you like my program. And please let me know if you want to see uh, the the functions that I am using to solve each problem, or you have any other doubts.